All right, so we've been talking about inclined plane problems and these kind of two-dimensional vector deals. So just as a quick review, we've been doing problems like this where there's some kind of inclined plane, some angle theta. Pretend that's straight. Some box with a mass sits on the plane. And last time we talked about, we're going to add in the fact that we have some frictional force here. So we're just going to say that our force friction acts that way. And we're going to say that our direction of motion is this way. So A, the box is accelerating down the hill. And we know now that this is pretty simple. We just have to find a marker that works. It's this one. So we just have to find some component vectors here. Starting with what we know is weight, which must be mg, but we got to deal with this normal force, and our direction that we've chosen for down, our positive x direction is that way, and generally our positive y direction is that way. So we have to account for this angle, and this is where you need your trig functions of sine, cosine, tangent. Ultimately, the way you solve all of these problems is just Newton's second law, knowing that the sum of all the forces is equal to the total mass of the system times the total acceleration of the system. So once we've set up this diagram, it's real easy to go through and find some things. So our forces in the x direction generally are going to be related to some function of this angle, which is usually the cosine of the angle times, in this case, wherever the weight is. And remember, we have this negative frictional force. And as a side note, remember the force due to friction is the coefficient of friction u times the normal force. We have to get the normal force from doing our vector process again. And then we just go add things up, being very careful to remember your signs and what direction you chose as positive and negative and how you have your axes oriented. We just go add the numbers, just go add everything together. And notice that we can do this without having any numbers at all. We can simply do this symbolically. In fact, it is going to be way, way easier if you work this symbolically first before trying to put in any kind of numeric values to anything. And the reason for that is because it's really easy to get lost in the into the signs and the negatives and the positives. What vectors point where, if you try to just start plugging numbers in immediately. Also, using the symbolic notation like this, we find that a lot of times things are going to cancel. In most cases, when we're trying to find, say, the acceleration down the hill, then we're going to find that our mass in a lot of cases cancels. It's really not going to matter. Another kind of problem you might do is, let's say we have a situation like this where there's some force due to friction that's trying to hold the box back. The box is trying to slide down the hill, but we are going to come in and apply a force, this F sub A applied force. And this is whatever we want it to be. So this is a guy pushing the box up a hill. And what we would ultimately like to find out is something like, what's the acceleration of the box up the hill? That's certainly going to depend on how hard we push the box. Notice we haven't really done much of anything here. This is just the force. So ultimately, that force, in order to make the box move, has got to be equal to total mass of the system times acceleration. But it also has to overcome the frictional force, or it actually has to overcome that X component of the weight force to start moving again. Now, in this case, what's going to happen is as you start pushing this thing up the hill, this friction vector is going to flip because you're going to change the direction of the box. That's okay. We just simply account for that with a sign. But what you'll find is that once you do all this vector stuff, and we find what the magnitude, we know the magnitude of our force, and what we have to set it equal to, so it's that X component of the weight, then that force equals MA, which equals whatever the X component of our weight is. We solve for A. Pretty simple. And then further, if we know A, we can solve, let's say I knew the length of this ramp. If I know the acceleration, then I can find out the velocity at some given point. If we assume that the ramp is X units long, we can just use our kinematics equations and solve for B. So not a big deal. What we're going to do today is introduce yet another kind of force that we might want to measure that you are probably used to dealing with in your everyday life, but you didn't really know that it was a physics thing you were dealing with. We're going to do something called the Atwood machine. I know you probably never heard of an Atwood machine, but you've seen one and you probably built one and you probably used one. All an Atwood machine is, let's say that we have some pulley. There's a rope going over the pulley, and we have a mass on each end of the string. So mass 1, mass 2. Those masses do not have to be equal. Depending on which one's heavier, you're going to get motion in the string. But the thing that's important that we want to study here is now, remember when we had the case of, just the simple case of box on the floor. Newton's third law tells us that every applied force has an equal applied force in the opposite vector. We call that the normal force. So in this case, if our weight is the mass times gravity, since this thing is not oscillating in the y direction, we know it's stationary. Newton's third law tells me there has to be an equal and opposite force. We call that the normal force, which is just the opposite direction of the weight force. This represents the box pushes on the floor with weight, the floor pushes back on the box with some normal force. But in this case, with our Atwood machine, we have the boxes are hanging from some rope, chain, whatever it is, and they're not touching the floor. But there is still a weight component to those things, obviously, because we're under the influence of some acceleration, in this case, the gravitational field. So where's the equal and opposite force if there's nothing to push back on it? Well, the equal and opposite force here is, you might have guessed, has to be in the rope. And we call that force tension. So what we're going to do is we're going to solve this Atwood machine problem in very general terms. So what we'd like to know is how much tension is in each of these ropes. Seems a useful thing to know. Why would I want to know that? Well, if I'm an engineer and I'm designing this machine, I want to make sure that I don't break my rope. The rope is going to have some maximum tension strength, at which point it's going to snap. So we want to make sure we don't exceed that. So we'd like to know what that tension force is in the string. Couple of assumptions that we have to make here to do these problems, at least for now. The first thing we're going to assume is that the rope has no mass. Okay, so we're not going to have to account for how heavy this rope or this chain is. If you did, it gets a little tricky because now you have more on one side than the other sometimes, and you have to account for that in a general manner. So for this example, we are going to assume massless rope. We are also going to assume that the pulley is frictionless. In other words, we're not going to worry about the coefficient of static or kinetic friction on the pulley. And the reason we're not going to do that is because we haven't looked at rotational motion yet. We haven't looked at circular motion. And those calculations are much, much different. We are also going to assume that the pulley has no mass. The reason we're going to do that, again, we haven't talked about rotational motion. There is a thing in rotational motion called rotational inertia that you would have to account for if this thing had mass. You have to overcome the rotational inertia of the pulley to make the system move. Because we're doing spherical cow and a vacuum kind of problems, we're going to make these assumptions. The rope has no mass, the pulley has no mass, there is no friction, and of course, spherical cows and vacuums, no air resistance. We don't care about the morphology of the masses. So the only thing we're going to deal with are going to be these two forces, the weight force and the tension force. So not too bad so far, right? Oh. Let's start doing some physics. Right? If you ever saw the movie The Martian, came out a few years ago with Matt Damon, And he has a line in there, he says, I'm gonna have to science the shit out of this. Well, that's what we're gonna do, we're gonna science the shit out of this. So we have this pulley. And we're trying to kind of model what's going on here. So we can do a couple of things. We might want to find out, for example, if we're given the mass of one of the blocks, and we know how fast the whole system is moving, then we might want to know what the mass of the other block is. Or if we knew the mass of both blocks, we might want to find out what direction the whole system moves in and how fast it moves in that direction. All kind of reasonable physics questions to ask. So since these are kind of reasonable, standard kind of physics questions, and since we have not yet moved on to our next kind of unit of big concept, it's a pretty safe assumption that we're going to solve this problem using Newton's second law. So the first thing we're going to do is write down our Newton's second law expression. Sum of the forces equal to the total mass of the system times the acceleration of the system. All right. Well, a couple of things become pretty interesting here. Notice I'm not dealing with any kind of angles. I don't have to worry about sine and cosine in these problems. I know a lot of you just breathe a huge sigh of relief for that. So we don't need sine and cosine to do this problem. But what we can do is we can say, if we look at one side of this equation, we already know a couple of things. We know that weight of one, W1, is just equal to whatever mass one is times acceleration due to gravity. We know that weight 2 is just m2 times the acceleration due to gravity. Well, we can solve this. The way you solve this is, instead of trying to do both things at once, what you want to do is just kind of split this thing into two problems. You solve side one, solve side two. It's got to be pretty easy. So let's solve for side one. For side one, we got the sum of the forces. Well, what forces do we have? We have weight 1, and we're going to call down our positive direction. And we have the tension. But notice the tension is in the opposite direction of weight, so we pick up a negative sign. That has to equal the entire mass of the system, which is just m1, times whatever acceleration it is experiencing. Notice I say whatever acceleration this is experiencing. This block may be moving in that direction, but not at the speed, at the acceleration due to gravity. Well, why is that? Well, because we have this other connected weight. So that's going to slow it down. Obviously, the way the system is drawn, if one of these sides moves down, because they're connected, the other one has to move up. Again, you've probably built this and you've seen this. If you go to the gym and you use the weightlifting machines, examine them pretty closely next time you see that. You have an Atwood machine, except you have more than one pulley. In fact, the more pulleys that you have, the easier it gets to lift the weight. So what are we doing in your exercise machine and a weight machine is essentially on the left side that you would be pulling down on, that would be, say, your pull down bar. It's connected through some pulley to a block of weights that you have some mechanical way to adjust how much weight is there. 50 pounds, 100 pounds, 1,000 pounds, whatever it is. And what you're trying to do is apply enough force to lift that mass. So that's all we're doing here. It's just an Atwood machine. Now, if you notice in those machines at the gym, a lot of times what you'll get is just a single pulley. And what that's going to do for you is basically makes the down force equal to the up force, which is what we're about to do. If you wanted to use this as a machine to help lift something, what you do is put multiple pulleys, and the more pulleys you put, the easier this is going to get. And we'll get to that in a little while, particularly when we start talking about energy. But for now, this is just simple pulley. We've got a rope, we've got some masses. One mass is pulling down, means the other one's going to go up. So for side one, we know that weight one is just M1G, because that's just the weight, right? The weight is just due to the mass and the acceleration due to gravity, minus whatever the tension force is. Well, I don't know what that is yet. And then, because Newton's second law, it's just M1A1, or A1 is just the acceleration of that thing. So that means if we solve for tension, which is really what we want, what we're going to end up with is something that looks like is M1G minus M1A1. There's our tension. Now we're going to do something cool. We can use this information to find what's going on with the second box. Now notice I said we're going to solve these as two separate problems. So we just solved for part one. If we come over here and solve for part two, without going through the algebra again, we'll find that tension 2 has got to equal M2G minus M2A2. Exactly the same process. Now is where we're going to have to do a little physics and a little thinking like a physicist. What can we say? What can we safely assume about the two tensions? Since we know that this rope is massless, we know the pulley is massless and frictionless, then the pulley might as well not even be there, right? We could easily duplicate the system both sides here. we could easily make the system look like this, right? Since we don't really care about the pulley. We don't really care about rotational inertia, anything like that. If you imagine these two blocks are moving basically opposite directions, right? They'd be moving away from each other in this case. Then the tensions point towards each other. And you can kind of just envision this, just look at it. Those tensions have to be the same. There's no way you're ever going to see a situation where you're pulling on this end of the rope and it makes a tension of, say, 100 newtons, and the other end of the rope attached directly to this other thing only has a tension of 2 newtons. That's not going to happen. Can't happen, right? Because notice, we didn't say anything about how long this rope is. Now, yes, there is a weird thought experiment that you can get into. If you think about an infinitely long rope, there must be some time for that force to propagate through that rope. And that has to do with density of the rope and things like that. And it gets really, really weird, really, really fast. We're not doing that. So we know that our two tensions must be the same. Well, if we know our two tensions are the same, since T1 equals T2, and we know what T1 is, 1G minus 1A, that's got to equal M2G minus M2A2, take one. Now I have a symbolic equation that allows me to find anything I want about the system, given enough information. We also know if we rearrange a little bit, just a little bit of algebra, if we rearrange all this stuff and we get our G's together and our A's together and what's A1 and A2, then what we're going to find is that the second mass has got to equal the first mass times the ratio of the gravity and acceleration sum and difference. So you might ask yourself, well, what in the hell happened to my A1, A2 subscripts on my acceleration? The same thing that happened to the T1 and T2 subscripts. Since T1 and T2 are the same, and this is a connected system, if one side is moving with a given acceleration, then the other side also has to be moving with that same acceleration, right? So A1 and A2 end up being the same. And so because of that, again, do a little bit of algebra, and you come out with this equation that your M2 is that ratio. This is the sometimes called the Atwood equation because it's an Atwood machine. Now, given this, we can now answer all kinds of questions about the system, right? If I say that this box weighs 100 newtons. And this box weighs 20 newtons. Then I can find out what the tension in the string is, right? I don't know what it would be, but we can figure it out real quick. Let's say this box is 100 newtons. Then our mg is 100. Our ma, well, it depends, right? If the box is falling under the acceleration of gravity and it is not connected to this thing, then mg would equal ma, right? If that happens, then you get T equals mg minus ma. If A and G are the same, T equals 0, there is no tension under free fall. Cool. That's exactly as we expect. But if we constrain this thing, and we say this box weighs 100 newtons, and it's falling at an acceleration of, let's say, 1 meter per second squared. Now, let's just, for the sake of argument, to make the math easy, let's call the acceleration of gravity 10 for now. So this is, and it doesn't really matter because I already said the weight was 100 newtons. So this becomes 100 newtons minus whatever the tension is. And we know the mass, well, we'd have to find it, right? So if weight is 100 newtons, then that's got to be the mass of the thing times acceleration due to gravity, we're going to call 10. So that means that M1 has got to be 10 kilograms. So that's 10. And if we said we're accelerating at 1 meter per second squared, then we get 100 newtons minus T1 is just 10 newtons, right? Because that would end up being kilogram meter per second squared. So 10 kilogram meter per second squared is 10 newtons. So do a little bit of algebra here, and we get 100 newtons equals 10 newtons plus T. So T must equal 90 newtons. Well, since tension is 90 newtons and those tensions have to be the same, then we can say 90 newtons has got to be equal to M2G minus M2A2. Well, in my imaginary setup, I said, well, what if this thing weighs 20 newtons? Well, that's my mg. I could do the same process, find its mass. And now the only thing I don't know is A2. Well, I could certainly find how quickly that thing's moving. It should work out to be 1 meter per second squared. If I didn't know how much that weighed, and all I knew was how quickly the thing is moving, then I could plug my numbers back in and find out what that mass is. So this is pretty useful. So, to recap, Atwood machines are just simple machines. All we're doing is sum of the forces. There's nothing new here. As always, let's draw ourselves a picture of what's going on, and let's label our vectors. Remember, this was just an example to remind you what normal force is. But in this case, there is no normal force. But there has to be some other force, right? There has to be this opposing force. And we're talking about connected systems and ropes and chains and things. We're going to call that tension. So we draw our picture, label our vectors, basically do our free body diagram, and then we solve two sides of the problem. Set up side one, side two. All of them solve with sum of the forces equal MA. Remember that this M is total mass of the system. So you may end up having problems where there's 4 masses or something. Maybe there's one big mass on the left side and 3 little masses on the right side. And they're going to be held together by some tension and force. And you can easily find that. There's a class some of you may take if you're in engineering called statics. And this is going to be really, really important to you in statics, because you're going to be finding stress and strain on like bridge components and things like that. So that's all we're doing is sum of the forces. What we're going to do next time is we're going to introduce the concept of those angles again. So we're going to do something different. Instead of the Atwood machine, we're going to do a tightrope walker, right? There's going to be a guy walking on a tightrope. The rope is going to sag in the middle, and thus it must have some tension to hold the guy up, and we're going to be able to calculate what that tension looks like. When we do that problem, we are going to assume nice straight lines. In reality, if you go out and you look at the tightrope walker problem, what you'll find is that the rope does not make this nice sharp angle. The rope actually makes some kind of bend, some kind of curve. And that is a very, very difficult problem to solve. So we're not going to do it that way. We're just going to estimate nice sharp angles. When you get into advanced mechanics, then you'll start doing the problem where the rope is curved and we need to figure out the path that rope takes and what that curve looks like. And that's certainly going to depend on the mass of the rope, acceleration due to gravity, lots and lots of other things. The bottom line is, in order to solve that, you need variational calculus. And since this is not a calculus-based course, and even if it was, the prereq would only be Cal 1 and variational calculus is a graduate level mathematics class, I can assume that you have had variational calculus, as fun as it is. So that is where I'm going to stop today. The homework assignments are up. They're going to be due Friday at midnight. They're going to cover everything that we talked about last week, plus these kind of problems and the tightrope problem that I'm going to show you next time. Questions?
Nope.
Okay, then I will see you guys next time. Remember, I am always available to you if you need it.
All right. Thank you.
Sure.
Thank you.